Good day, ladies and gentlemen. The topic of my presentation is geometrization of Kryvbas iron ore deposits. The purpose of my talk is to illustrate this question. Ukraine ranks third in the world as to calculated iron ore reserves, which make over 62 billion tons. Most of these reserves, over 32 billion tons, are concentrated in Kryvbas iron ore basin and mined by open pit and underground methods. According to the U.S. Geological Survey, during the past 15 years, Ukraine ranks sixth in terms of the amount of the ore mass mined, 70 to 86 million tons per year. To maintain a high level of annual ore production, mining enterprises are continuously enhancing technological processes. The purpose of the study is geometrization of the iron ore deposit. A particularly important aspect of geometrization of iron ore mineral deposits involves mining and geometrical prediction of their quality indices to solve problems of long-term and current planning intended to provide the most efficient performance of mining enterprises in terms of ore blending and increase rationalization of deposit development. The most promising methods for assessing indicators of the deposit include geometrization ones based on the use of a set of self-organizing methods and geostatistical methods of assessment, which are developed and enhanced in the present work. Processing the initial geological data requires a lot of sampling. The content of samples influences the quality in a certain block or area of the deposit. The problem of sampling is associated with application of various methods for determining weighted averages. According to figures 1 to 6, at Skelevatsk deposit, the minimum critical interval of geological exploration for both magnetite and total iron is 600 m. This enables the conclusion that parameters of the exploration grid meet the requirements to them. The following two aspects of the problem are of great importance: the search procedure and a criterion for its completion. This criterion can be based on the value of the distance from the sample to the block or to the point where the composition is to be determined. In the most complex programs for calculating weighted averages, the search for points in an area is carried out on a plane or in a cone to ensure relative representativeness of all directions. This enables avoiding the effect of accumulation of samples in certain directions and their absence in others. This step is, however, superfluous in case of kriging, since with accumulation of points, introduction of sample covariances allows considering automatically the influence of components of the cluster, eliminating its excessive influence. Kriging helps to distribute weights among the nearest samples, if a constant density of sampling is not provided. A sample removed from the block in a given direction for more than an influence interval, if any, is assumed to have a zero weight and should not be used. As an example, let us assess the exploration grid of Skelevatsk deposit of ferruginous quartzites mined by the Pysmennyi open pit. The best method of assessment for actual conditions of Kryvbas iron ore deposits can be chosen by comparison. First, dependency of the natural component of variability on the sampling interval is assessed, and then autocorrelation coefficients are determined at different sampling intervals. As is seen from figures 7 to 12, the autocorrelation coefficient provides ambiguous results. This is due to the fact that this coefficient inherently estimates, to this or that degree, deviation from the sample average value. The deposit has for a long time been sampled in two ways. Detailed exploration is carried out by sampling the sludge of boreholes located irregularly with an interval of 50 to 200 meters. Operational exploration is carried out in the exploded mass by the point method. In case of homogeneous ores, pieces from an area of about 50 meters long, in the direction parallel to the bench slope, with the width determined by the size of the block to be exploded, are selected in one sample. In case of heterogeneous ores, each type of quartzites is sampled separately. Thus, in order to qualitatively assess a deposit with a nonlinear nature of index variability, the volume and interval of the sample should be selected with great accuracy, and the initial data should be smoothed over as well, this being very time-consuming and not always possible. In this very case, the graphs are sine curves with a growing amplitude. Deviations of the indices of nearby points from the average also change in the close to sinusoidal manner, so the deposit can be said to actually have a sinusoidal component when obtaining the indices, and the autocorrelation coefficient is not quite relevant for assessing the exploration grid of Kryvbas iron ore deposits. The experiment was carried out at the Peremetchyk open pit. 3 equations of predictive functions are presented in figures 13 to 15. The most important geological and technological indices of ores of Skelevatsk deposit of ferruginous quartzites include the content of magnetic iron, which is associated with the total iron content. The nature of magnetic iron content in the exploded mass can be predicted based on the borehole sample data. At that, it is advisable to take the content of total and magnetic iron according to borehole sample data as arguments of prediction. Argument values in the interhole space can be determined through interpolation. It is advisable to use kriging as an interpolation method. The content of total and magnetic iron by detailed exploration boreholes data and horizontal and vertical coordinates of the centers of the sampling areas were taken as arguments for prediction using the multidimensional heuristic prediction algorithm. With the help of kriging, isolines of the content of magnetic iron in the interhole space were built. In the center of each sampling area of the exploded mass, the value of magnetic iron was determined based on the available electronic model of isolines. Based on the interpolation, there were built plans of isolines of the predicted magnetite iron content, which are presented in figures 16 to 18. Predicted data for current planning was received by adjusting the obtained electronic model according to operational exploration data at points spatial position of which was determined on the basis of production needs and was irregular. As a result of the study, an effective geometrization technique has been developed that meets the requirements of mining production. It enables assessment of mineral reserves and significantly increases efficiency of planning mining operations. The use of geostatistical methods makes it possible to assess and process the initial geological data. The developed self-organizing prediction algorithm is flexible in application, efficient, and can be used in various mining and geological conditions for geometrization of the deposit in order to provide planning and assessment of various mining technologies. The relative error of the predicted value of the magnetic iron content in the exploded mass according to the developed method for long-term planning does not exceed 6.8%. The positive results of prediction at the area under consideration are the basis for using the developed methods in other areas of the Peremetchyk open pit. Proceeding from the results, methods of geometrization of mineral deposits based on self-organization and geostatistical assessment are a very promising direction for further research. The considered methods require further development and enhancement in order to increase their efficiency and application at deposits of Kryvbas as well as other regions that produce both ore and non-metallic minerals. Well, that's it from me. Thanks very much.